anyone has any questions, oh, if anyone has any questions, please send them either to the chat here or in the what do you call it?
Slack.
Slack. Yes, I'm losing words. I hate Slack, so trying to ignore them. Anyway, so our first paper will be presented by Pushpraj Naik, and the paper title is Network Data Remnants Side Channel Attacks on Spread, H-Spread, and Reverse AODV. And Pushpraj is a final year Master Technology student at the Computer Science Department IIT Kanpur. Pushpraj, please, the stage is yours.
Hello. Hello.
Yes.
Yeah,
Sorry.
Okay, sir. So good evening, everyone. My name is Pushpraj Naik. I'm final year MTech student from IIT Kanpur, and today I will be presenting network data remanence side channel attack on two secret sharing schemes named spread and net spread, and one routing protocol which is reverse AODV. I am also joined by my supervisor, Professor Urbi Chatterjee. So side channel attack. So these are any kind of attack that are based on information gained from the physical implementation of the process or system rather than the theoretical weakness in the algorithm. So we have broadly four type of these side channel attack. First one is a timing based side channel attack. In this side channel attack, what adversary does is it carefully measures the time required for secret key operation, and then it can relate that timing with the key, and it can take advantage and can also help. This can be used in reducing the key. Another kind of side channel attack, which is known as power attack. So here the adversary measures the power consumption of the hardware platform running the cryptographic algorithm, and then it tries to relate it with the secret key. Next is electromagnetic attack. So this here the attacker captures the electromagnetic radiation emitted by the systems during the cipher operation, and this with the help of devices like EM probe, and it can deduce the secrets. Another attack which is also widely used is fault attack. Here the attacker manipulates the hardware device using abrupt changes in voltage, and it produces some glitches, and then it can use the modified output to know the key. So are these the question here is are side channel relevant? So so the answer is yes, and uh, we have also seen some recent means attacks in the recent past. Like first one was attack on Telegram messaging protocol. So there were four attacks. One of them was a timing-based side channel attack. Here the adversary measures the sends multiple messages and records the timing needed. Means time needed to deliver the message, and then uses those information to know the plain text from ciphertext. And another example can be the Intel XGS exam, where researchers from University of Birmingham uh, made a very inexpensive device, uh, which takes advantage of the fact that there was a separate uh, uh, power voltage, means they can change the CPU voltage through that device, and they can launch power side channel attack. Similarly, there was also attack on some vulnerable smart cards. So this was also a side channel attack. Here, the attacker only needed 30 minutes or so to get the secrets from the smart card, and then they could spoof any smart cards. So another was also a side channel which was ladder leak. So it also improved the existing attacks on ECDSA cryptography. So these are some relevant side channel attack which we have seen in recent past. So next question is, are side channel only relevant to hardware platform? So answer is no. The side channel can also, the concept of leaking data can also be extended to wireless sensor networks, and this forms the base of our paper, which is and one such attack is network data remanence. And so before going to the network data remanence part, we need to know two concepts, like first is secret sharing. So secret sharing is essentially the building block of for many applications like secure multi-party communication, distributed storage, and side channel protection. Here, the sender divides the secret into multiple parts. Let us say the sender has divided the secret into n parts, and then it sends those parts to the receiver. So it consists of two parts, like a randomized secret generation algorithm, and another is deterministic construction algorithm. So at the receiver can pick any t shares out of n, and then it can reconstruct the secret. So this is called t and secret sharing scheme. This scheme is secure until unless the attacker has uh, uh, at most t minus 1 shares. So if attacker has any less than t shares, so it cannot reconstruct the secret. Another scheme which is essential for our paper is multipath switching with secret sharing. So here the assumptions are the sender and the receivers are connected by n wires, and the adversary can monitor k paths at a time. K is less than n, and adversary is mobile, meaning it can switch the paths which it is listening to. So for example, here n is equal to 5, meaning there are 5 paths, and uh, k is equal to 3, meaning we are sending data on any of the 3 selected paths. So how this works is, sender generates share using KK secret sharing schemes, selects any k out of these available paths, and then it sends the secret along those paths. So network data remanence come into the picture uh, because the multipath switching with secret sharing schemes uses two assumption, which is the path between the sender and receiver are atomic, meaning there is a direct path, and all the paths have same delay. So these two assumptions are very means they are far from reality, and these do not hold in real networks, because there are paths because paths are all multi-hop, and path can have multiple delays. So these create an environment for the shares sent by the sender to linger in the network, and then the adversary can take advantage of that fact, and it can capture those shares and reconstruct the secret. So now we will introduce you to the attackers that take advantage of the this NDR side channel. First is NDR blind attacker. NDR blind attacker is a attacker which randomly chooses any k out of all the intermediate nodes present between the sender and receiver. For example, we can say here there are 5 paths, and each path have 3 intermediate nodes, and we are sending the shares on these three paths. Initially, at the first tick, uh, these three nodes have the data, and the NDR blind randomly has selected these three nodes, and it is listening to these three nodes. In the next tick, what will happen is the share will travel to the next hop, and at the same time the attacker will listen to means next three randomly selected nodes. So similarly uh, it does this process till the shares are received by the receiver. So there are 15 C3 possibilities which the NDR blind attacker can make. Another attacker which takes advantage of NDR side channel is NDR planned attacker. So this is a little more sophisticated attacker than NDR blind attacker, as it does is for at the first tick it selects node, means k nodes, from all the nodes which are present at a distance 1 from the sender. So we can see here in the example that these three nodes are containing the shares, and the attacker is monitoring these three nodes which are present at a distance 1 from the sender. So in the next tick, the attacker will now capture k nodes from all the nodes which are present at a distance 2 from the sender, and the shares will be present in these three nodes. Similarly, it continues, it chases the share until the shares have received by the receiver. So this is a little bit more sophisticated attacker than NDR blind attacker, as it uh, travels along the share and chases them. So NDR, we can see the uh, the plots for these two attackers, like for a single message, and we have measured the probability of capturing k shares, and we can see that NDR blind attacker, which was randomly selecting nodes from all the intermediate nodes, is less effective as compared to the NDR blind attacker, as the probability maxes out at 0.14, and NDR planned attacker, which is a more sophisticated one, can take advantage of the fact that uh, as the path length increases, its chances of recovering the data also increases. So this here on there was seven paths between sender and receiver, and for different values of L and K, the values are plotted here. So our contribution was exploring NDR, and for our paper we have identified two secret sharing schemes and one routing protocol, and we launched the NDR attack on them. First one was secure protocol for reliable data delivery spread. Another was H spread, which is hybrid secure protocol for reliable data delivery, and third is reverse AODV. So we'll start with spread. Spread spread is a mechanism that is used in mobile ad hoc network. Mobile ad hoc network are self-configurable, infrastructureless, multi-hop wireless networks. These have many application, they are used in many settings. So these are important. And what means what is used in spread is this is similar to other traditional secret sharing scheme. It also splits the share into multiple parts, and then it selects k random paths, and then it sends the share on those paths. So in spread, what happens is the path once selected to deliver the shares do not change with the next messages. So it is once we have identified a path to send the shares, the path remains same. uh, the next topic of our paper was edge spread. This is used in wireless sensor network. So wireless sensor network typically consists of many low-cost sensor node, which collectively senses some physical process, and then it sends the data to the uh, base station. And the uses of these are in sensing nuclear plants, mines, real-time traffic monitoring, weather monitoring, etc. So typically, these sensor nodes are low. Means they are resource constrained in terms of power and computational capabilities. So they can't use traditional cryptographic algorithm for secure data delivery. So they uses this edge spread scheme. What happens in edge spread scheme is that the base station initiates the route discovery process, and the end-to-end multipath route discovery protocol is used to find multiple paths between the sender and the base station. And then it uses the data delivery mechanism, which also uses secret sharing, which divides the data into n shares, and it delivers the data using those using all the multiple paths. So the to launch NDR attack on this scheme, the main intuition was the once the sender has selected the path to deliver the first message, the sender do not select new paths for the subsequent message. So for this analysis, we have assumed that the in both the schemes, we have computed multiple path between sender and receiver. So sender has n node disjoint path between means we have n node disjoint path between sender and receiver, and each path is at least three hops long, and the sender uses k and secret sharing scheme to transform the message into k shares. Now the adversary model used here is that adversary can monitor the nodes and capture the shares at switches, and we further assume that it takes one tick to move from one hop to another. So NDR blind attacker, as discussed earlier, randomly selects k intermediate nodes from all the intermediate node present between sender and receiver, and uh, it randomly listens to those those nodes. And another attacker, which was NDR planned attacker, which was a more sophisticated one, uh, it selects k node which are so in the first tick it selects k nodes which are a distance one from the sender, and gradually with the subsequent ticks it moves towards the receiver following the shares. And whenever it reaches the receiver, it again goes to the nodes which are at distance 1 to capture the shares of the next message. So to the equations for NDR blind attacker can be seen here. Uh, here P m comma 1 gives the probability of capturing m shares in one tick. So we needed k shares to reconstruct the message, and our total number of path here is given by n, which is the total number of path the sender and receiver have. L is the path length. So we can see that out of k, we have to select uh, m nodes, and we can select the rest of the nodes, that is k minus m, from the remaining intermediate nodes. So we can generalize this uh, for t ticks, and which is given by this equation. So here the second part of this equation gives the probability of capturing I shares in one tick, given that m minus I shares will be captured in t minus 1 ticks, and we can use this recursive formula to get the overall probability, and our goal is to capture k shares in L minus 1 ticks, because we have assumed that uh, it takes one tick to travel from one node to another, and the path length between the sender and receiver is L. So at most L minus 1 ticks will be needed to deliver the shares. Similarly, equations for NDR planned attacker for spread and S spread can be seen here. Here also the probability P m comma 1 gives the probability of capturing M shares in for 1 tick, and we can generalize this to for T ticks. Here also second term of this equation, which is given here, shows the probability of capturing I share given that in one tick, given that M minus I share will be captured in the remaining T minus 1 ticks, and we can use this formula to calculate the probability of NDR planned attacker. Here we see the plots of these two attackers. These two plots are for single messages, and we have used 7 disjoint path between the sender and receiver. NDR blind attacker is less effective as it only captures it does not use means it the probability does not change with the increasing path length. It remains almost constant, whereas NDR planned attacker uses means exploits the NDR side channel well, and with the increasing path length the probability also increases. With these two schemes, spread and edge spread, since they don't change the path with the subsequent messages, so after doing this much of work, the adversary now has a knowledge of the which path are used for sending the messages. So from the next message onwards, the adversary can listen to only those paths which carries the data, and it can capture the remaining message stream with probability 1. The third use case for our paper was reverse AODV. It is a routing protocol used in mobile ad hoc network. So here, when the sender needs to send data to the destination, it broadcasts a message that is a route request message, and the all the nodes broadcast that message until it reaches the destination. And when the when this message route request reaches the destination, it broadcasts a reply till to the sender, and the sender captures the reply and builds uh, multiple paths between the sender and the destination. We can see here. So in this scheme, we do not break the message into shares. It does not use secret sharing. Instead, it sends one complete message in using means one. It changes the path for different messages. So for first message, it may take one path, and for the next message, it may take different path. So multipath switching is used. So here also we can apply NDR attacks that are NDR blind and planned. So our goal here is to capture only one share, because we are not breaking the message into shares. You are within T ticks. This can be given by this equation. Here Q is the probability of capturing. So here the attacker does what it does is it captures. So for NDR blind attacker, it randomly selects one node. So two things can happen for that node. One is the selected node is carrying the data, so whose probability is given by Q, and if that happens, then our task is now reduced to capturing 0 packets in the remaining time, which is essentially 1, because our task is done since the message is not broken into shares. But what other thing can happen is we have the node selected does not carry the data, which can happen with the probability Q minus 1, And so our so our task is now reduced to capturing to capture one node with the remaining time t minus 1. So this we can apply this formula, and for NDR blind attacker, um, the value of q will be 1 over all the intermediate nodes, as it randomly selects nodes from all the intermediate nodes. And in case of NDR planned attacker, the probability q will be given by 1 over n, because it systematically listens to the node present at distance 1, and then subsequently it listens to the node which are at distance 2, 3, and so on. So at every tick, it will listen to n nodes, and 1 over n is the probability given by probability for NDR planned attacker. Here are the results for NDR blind and planned attacker. NDR blind attacker does not exploit this side channel well, so it is almost constant. But NDR planned attacker, with the increase in path length, the probability of recovering data also increases. So these plots are for a single message, and the path for every message change, and we have considered 7 node disjoint path between the sender and receiver. So to conclude, in this work, we have identified 2 secret sharing scheme, spread and spread, and 1 on-demand routing protocol, reverse AODV, and we have launched NDR attacks on this. All these 3 cases are vulnerable to NDR blind and planned attacker. Although NDR blind attacker is less effective, but NDR planned attacker can be a great challenge for network protocol designer. So with the ever increasing size of wired and wireless network, this attack can be prevalent, as this is a this scheme can be very useful for lightweight alternate. This can be a lightweight alternative to encryption algorithm. So with this, I will conclude my presentation. Thank you.
Thank you very much for your talk. Do we have any questions? Well, people are thinking of question or writing the question. I wanted to ask, in typical networks, the number of potential paths may increase exponentially with the number of nodes. So how do you design an attacker to handle the increased number of paths?
Yes, sir. There can be multiple paths in a realistic network. So means out of this is advantage for the we can use multiple paths to deliver the message. And so for our analysis, we have considered that there are n paths, and we have done the analysis.
Okay. Any further questions? Okay. We don't seem to have any questions, so thanks, Pushpraj again. And we'll move to our next presentation.
Thank you, sir.
And our next paper is about the title is Parasite Mitigating Physical Side Channel Attacks Against Neural Networks. And the paper is presented by Linda Guiga. And Linda is a PhD student at Telecom Paris, and in Idemia. He's been there since late 2019, and he has been working on protecting neural network models against reverse engineering attacks. Please, share the screen. Look forward.
Sorry. Okay. Can you see the screen and can you hear me?
All working, thank you.
Thank you. All right, so I'm going to present Parasite, Mitigating Physical Side Channel Attacks Against Neural Networks, which is a paper that aims at basically protecting neural network parameters against physical side channel attacks, and more specifically, we focus in this paper on electromagnetic-based ones. So why would we want to protect neural network parameters? So we all know that neural networks now are part of their daily lives. We just had a keynote presentation on AI. They're present in our smartphones, in biometrics, medical field, they're used everywhere. But given a neural network architecture, finding the correct parameters, the optimal parameters, takes a lot of time and a lot of computational resources. And therefore, the parameters constitute intellectual property. But more than that, if an attacker knows the full model, the architecture and or the parameters, then other attacks can be launched, such as gradient-based adversarial examples, that they're much easier to carry out with the full model, which makes finding a small, an adversarial attack, consists in finding a very small noise that is undetectable by an oracle such as the human eye, but that still fools completely the model's predictions. And so this could lead, for instance, to impersonation attacks. Another kind of attack that's made easier is the membership inference ones, where the attacker finds out whether a certain input is part of the training data set. And this is a major security risk for the sensitive data. But the problem when it comes to protecting neural networks and machine learning models in general is the number of parameters. Often there are over 1 million parameters to protect. So common countermeasures are very difficult to apply. So that's why we consider an attacker that knows the architecture and aims at finding the parameters through electromagnetic traces. And we try to thwart this not by exactly protecting. So we want to protect the parameters, but not exactly by masking them or anything like that, but by adding parasitic model at the entrance dynamically. I will explain what that means, to mitigate the attack. But first, I'm going to talk a bit about the background. So what are neural networks? They're algorithms that are trained to carry out a specific task. They can be represented as graphs, where the nodes are the neurons and the edges are the weights or parameters. They're comprised of several linear models, each followed by a nonlinear activation function. So the most common, the easiest layer rather, is a fully connected one where each neuron is equal to the previous neurons multiplied by their associated weights. But the one that we're more interested in here is a convolutional layer, which requires much fewer weights, and they're often used in image classification or analysis. So here we only have a filter of weights, a small filter of weights that is convoluted with the input. So if the input is multidimensional, so is the filter, and if the output is multidimensional, there are several such blue filters here. If a model is mainly constituted by convolutional layers, then it's called a convolutional neural network. So now on to the side channel attacks that we consider in our paper. So simple electromagnetic analysis. So the attacker only needs one electromagnetic trace of a run of the target algorithm here to determine the secret information they need. So for instance, the attack we focus on here is CSI neural network written by Patina et al. And they use this to determine the number of neurons in an architecture. So here, for instance, they just needed one trace of a run of the model, and they could divide the trace into groups, as you can see here, and each group of computations, of each block of traces, basically, corresponded to one neuron. So they could count the number of neurons in the architecture. But they couldn't really differentiate between layers, and that's where they needed the correlation electromagnetic analysis. And here the attacker needs more EM traces and a tool called Pearson correlation coefficient that computes the correlation between two traces. So it's equal to the covariance between the two traces divided by the square root of their multiplied standard deviations. So in our case, to recover the parameters, they considered the individual multiplications between a given weight and a known input, and they wanted to recover, of course, the weight W. And they had, so as needed in correlation electromagnetic analysis, we need a function f that simulates the electromagnetic emanations for the operation that we target. So we can consider, for instance, the Hamming distance. So what the attacker does here is that they consider all possible weight values, and they compute the emanation, the simulated emanation, electromagnetic emanation for each such hypothesis and for each input, which gives them several traces. Then they can correlate the trace associated to each hypothesized weight with the original observed trace, thanks to the Pearson correlation coefficient, and they take the hypothesis with the highest coefficient. And so this is what, as I said, a CSI neural network does to recover the entire model. So, this attack represents a major security risk. So here, their attacker does not have any prior information about the model. The attacker just has query access, and they can acquire electromagnetic traces. And of course, they try to recover the architecture and the parameters. So the first step in their attack is to apply the simple electromagnetic analysis as I detailed before, which gives them the number of neurons in the architecture. And then they proceed layer by layer. In the first layer, they already know the number of inputs because it's the input image. Sorry, the number of neurons because it's, well, the input. And they just have to recover the weights as described with correlation electromagnetic analysis. But then for later layers, they consider for each neuron and the associated multiplications. Well, they hypothesize not only the weight, but also whether the neuron is in layer L, the current layer, or the layer L+1. And once they find a neuron that is in layer L+1, they can move on to the next layer. And for the activation functions, they use time analysis. Although there's another paper actually that also manages to recover the activation functions through electromagnetic analysis. Well, in our case, we consider a stronger attacker that already knows the architecture. So all they want is to recover the weights. So they don't need the they don't need the step where they determine the activation function anymore, and they also don't need the simple electromagnetic analysis anymore because they already know the architecture. But the rest is similar. They just, I mean, they also don't need, of course, they only need the hypothesis on the weight. So our countermeasure is, as I said at the very beginning, to add a parasitic model at the entrance of the target neural network. This model is going to approximate noisy identity. So they are pre-trained. We have actually a set of pre-trained parasites that are trained to return, given X, to return X plus a certain noise, a Gaussian noise with a certain standard deviation. And in our set of pre-trained parasites, we have various architectures, various weights because of different initializations, and also various standard deviations. And then, instead of always adding the same parasite at the entrance, we change the parasite at each run. So at each run, we randomly select a parasite from the pre-trained set and apply it at the entrance. So here we have a representation of the scheme. So we have the pre-trained set here, P, and at each run we select one parasite at random from the pre-trained set, from the pre-trained parasites, and apply it here at the entrance of our model. So the input first runs through the parasite, then through the model. So why do we do that? Well, first of all, because we can, in the sense that neural networks are not cryptographic schemes. They don't require exact outputs. We can slightly change the output without the accuracy dropping at all. Or, I mean, we can also accept a small drop in the accuracy as long as it still remains acceptable, of course. Moreover, here the attacker requires the correct input to recover the first layer's weights. And there's also a domino effect in the sense that if they got the wrong weights for the first layer, then the next layer is also going to be impacted because the output, I mean, the input of the next layer that they're going to get is a noisy one because of their wrong extracted weights in the first layer. Etc. And so the extracted weights are going to get worse layer by layer. And so if we manage to add noise in the first layer, then basically we can mitigate the attack. Then we want it to be a dynamic addition because we don't want the attacker to be able to approximate the parasite. I mean, we saw that in CSI neural network, the attacker is also able to recover the architecture and the parameters, I mean, the architecture and parameters of the model. And so if it's always the same parasite, then they can just apply their method to the whole new protected model. And we don't want that. So at each run, we changed the parasite. And finally, we consider a convolutional neural network. First of all, because, as I said, convolutions, for instance, are more weight efficient than fully connected layers. And also, we consider a model rather than just noise, because it's also more efficient in the case where the attacker does not know the architecture, because they have an architecture that's constantly changing, basically. So to evaluate our method, we considered two simulations. So in both cases, we just allowed the attacker to receive the output of the individual multiplications W times X, where W is the weight and X is the input value. So it's basically that we're supposing that the traces they have are perfect. So in the first simulation, we just wanted to evaluate the impact of an added noise to the model, and therefore the parasite that we considered was always the same, but the attacker did not know of its existence and just tried to approximate the target model directly, whose architecture they know. And so basically they receive the outputs W times X prime, where X prime is the noisy input, but they still use the original clean input X to recover the extracted weight. So we made several experiments for this simulation, and there's more in the paper. Here, for instance, we can see that when we increase the standard deviation or increase the number of parasitic layers, both the accuracy of the protected model tends to drop a bit. and the extracted accuracy drops even more. So one interesting value here, for instance, is if we take a parasitic layer with one convolutional neural network, with one convolutional layer, and standard deviation 0.2, see that the accuracy does not drop much from 71.44 to 70.23%, but the attacker does not manage to recover the model at all. We also try to study the mean differences between the original and extracted layer, just to see how the weights evaluated from one layer to the next. And what we did here, for instance, is so for the difference between the extracted weights and the original ones, we can see, so here the top two are for a standard deviation of 0.01, where the attacker could extract the model, basically, whereas the bottom two are for standard deviation of 0.1, where the attacker could not extract the model. And we can see, first of all, that these correspond to the first two convolutional layers of a mobile net v2 neural network. Mobile net v2 is a relatively small neural network in the sense that it was made for mobile phones, but it still has over 1 million parameters. So for the top two, we can see that from the first convolution to the next, so in the first convolution, the attacker could recover basically all the weights, but in the second, the noise started appearing and having an impact, since the weights are farther from the original ones. And that makes sense thanks to the domino effect that I told you about earlier. And when we compare top to bottom, we also see that with the increased standard deviation, the attacker has more trouble recovering the correct weights, and the weights get further from the extracted weights get further from the original ones. We can also derive similar conclusions by looking at the Pearson correlation between the original weights and the extracted ones. So then in a second simulation, we just try to check that if the parasite was no longer fixed, but dynamic, and the attacker did know about it, they still couldn't recover the original model. So this time, at each run, we selected a random parasite, and the attacker tried over several traces, 128 or 124, and they tried to recover the averaged weights of the parasite, as well as the actual target weights. And we see that we applied this to a LeNet architecture, which is a very small one, and again, mobile net v2. And in both cases, the attacker could not recover the correct parameters. In mobile net v2 here, we see there's a drop in the accuracy, but by better tailoring the parasitic models to the model, we believe that this could be fixed. Then we also computed the overhead by computing the number of multiplications that were added. So basically, for one convolutional layer, we add the size of the filter times the size of the output channel times the number of input and output channels times the total number of times the number of input channels of the model. We also adapted that to several parasitic layers, and what we see is that for just by adding two convolutional layers, we have 5% of the original mobile net v2 number of multiply and accumulate operations. So it is a relatively small overhead. So lighter than masking or shuffling independent operations, for instance, as suggested in several attack papers. And another advantage of our method is that it is based on pre-existing libraries such as PyTorch or Keras, since we're just adding a neural network model. And therefore, we don't need really intricate individual optimization tricks, and we can rely on optimizations to those libraries, and we benefit from any optimization from those libraries. So to conclude, we suggest a countermeasure that is, well, lighter than common cryptographic countermeasures, such as masking all of the operations, all of the independent operations, or shuffling. And although we only consider here one electromagnetic attack, we believe that this method could be applied to any physical side channel attack that relies on the sequential execution of the model and the knowledge of the input. We could also consider increasing the number of parasites. We don't need to add only one dynamic parasite. We can dynamically add several ones, as long as the accuracy doesn't drop too much. We could also try approximating the activation functions. And finally, we could try to better tailor the parasites to the models at hand in order to achieve a better balance between security and accuracy, model accuracy. We can, for instance, change the hyperparameters of the model. Well, thank you for your attention. Sorry.
Thank you very much, Linda, for your presentation. I do not see any questions, but for now, I have a question. In your second experiment, you mentioned that you do try to average the error out, or the parasite out. And I was wondering if the attacker has enough samples, wouldn't they be able to average out? Or
yes, we believe that it is the case. I mean, even for the first simulation in the paper, we mentioned that by taking more traces, the accuracy does get better. So we do not say that it is very efficient against statistical attacks, but the number of traces required to get the actual the original model also depends on the types of the parasites that we have, the number of parasites. So if we increase the number of pre-trained parasites, we can also increase the number of traces required to actually recover the model. So we can play with that to increase the security, basically.
Is there any relationship that you've noted between the number of, or the number of parasites that you add and the number of traces that are required? So,
so we did not note a particular correlation, but I mean, we had, for instance, we had a set of 30 parasites, and the attacker still struggled with over 128 traces to recover the extractor model. So I think the number of traces still increases a lot. So it does mitigate the attack, it makes it harder for the attacker.
Oh, sounds interesting. Particularly if the number of traces grows significantly, like linear increase in the number of parameters results in exponential increase in the number of traces, that would be a really interesting result.
Yeah, this is something we should check, I think, just to see how many traces exactly we need to.
Yeah. Oh, thank you.
Thank you
very much. I don't see any other questions, so thanks again. And we will move to the third talk today. And our third presentation is the paper title is Reinforced Learning-Based Design of Side Channel Countermeasures. So we continue with Countermeasures Side Channel. And this presenter is Lichao Wu, who is a PhD student prestigious in the cybersecurity research group in TU Delft, and he's also works as a security evaluator at SGA's Brightside BV. Lichao, please.
Thank you, Yuval, for the really nice presentations. I assume you can see the slides and hear my voice, right?
Yes, thank you.
Yeah, perfect. Thank you. Hello everyone, and welcome to this presentations. Today I'm going to talk about our recent work, reinforcement learning-based design of side-channel countermeasures. This is a joint work with Jorai, Rijsdijk, and Guilherme, Perin, and we come from Delft University of Technology, the Netherlands. So I assume some of you may know about the side-channel analysis, but let me give a brief introduction about that. So assuming that we have the hardware running the encryption algorithm, we input the plain text and we can get the output ciphertext. However, when doing these executions, we may have the side-channel leakage, and the leakage may come from the power consumption of the hardware or the electromagnetic emissions. And by doing the statistic analysis between the leakage value and the real data being processed, we can kind of retrieve the secret information, and we call it side-channel analysis. There are many ways to perform the side-channel analysis, and one of the most powerful approach is to do the profiling side-channel attack. It is really similar to the classification in deep learning. So basically there are two phases. The first phase is doing the profiling. We assume attacker have the clone device that he can have the fully control of. So he can retrieve the profiling traces and the related label, we call it profiling labels. And he can use the profiling model to build, to map the relationship between the profiling traces and labels. And then he just acquire the traces from the attack device that he want to retrieve the secret information, but he doesn't know about that. So he acquired the leakage traces from the attack device and send it to the profiling models and ask the profiling model to do the predictions. And finally, after some post-analysis, the secret information can be really easily retrieved. So for the profiling side-channel attack, there are many ways to do that. The two popular ways is template attack and deep learning attack. And this paper we mainly consider deep learning attack because it's really powerful in the recent literature. So yeah, we know that there are many ways to break the target by monitor the leakage from the hardware. So the developer or the hardware designer want to protect their side channel, mainly their side channel leakage. So how are they going to do that? They just add the countermeasures to the leakage, to the hardware, and the leakage may be obscure. Basically, there are two ways to do the countermeasure. The first one is hiding, another one is masking. So the hiding is kind of, you can imagine that you can you just add noise to the leakage, and because the leakage traces become noisy, then it becomes hard to classify. Another one is masking. So masking just do the random shares to the intermediate data being processed and just to randomize the data being executed. So the corresponding side channel leakage will be random, though the classification will be difficult as well. So these two methods are both used in academic and industry, and they are proved to be really effective. However, designing such a countermeasure is not really an easy task because we want to balance the effectiveness of the countermeasures, but we do not want to add too much overhead to the hardware. Imagine that we can add a countermeasure that is super strong, but it just consumes tons of the powers from the hardware. Then it's not feasible for the modern device, especially you want to use it in a mobile phone or want to use it in a smart card. So our questions or our motivations of this paper is to how to design a cost-effective countermeasures. So you can say that I highlight the cost-effective. So we consider in two aspects. The first is the cost of the countermeasure, and also another is effectiveness of the countermeasures. How much security level the countermeasure can bring to our hardware. So to design such a countermeasure, we use reinforcement learning and more specifically, the Q-learning. So basically the objective of the Q-learning is to maximize the reward of an agent by taking a series of actions. in response to a dynamic environment. So maybe you can see the later point here. So we have the two objective. The first one is agent, and another one is environment. So basically, we're just doing the interactive process between the agent and the environment. So let's start from the beginning. So the environment will first give the state to an agent, and agent based on the current state, the agent will take an actions. And the actions, this action will influence the environment. And based on these actions, the environment will output the reward of these actions based on the current state. And also because the state has been influenced by the current actions, the new state will be generated. Then the loop starts and start again. So as you can see here, by calculating this reward based on the state and actions, the agent can knowing better and better about the environment. And finally, the agent can reach the objective by knowing this environment. So I have another example to better show you how Q-learning works. So here, assuming that we stand in the middle and we want to go to the right up corner, which is a green block. So basically, we have four, the objective is going to the right up block and with the highest reward. So you can see that for each block, we have the reward. It could be either 1 or -1. So basically, there you have four directions to go. So based on your choice, it will update your current state, and also because you are moving left, for example, and you can generate actions. So we use a Q value, which is also Q learning here. We use a Q value to evaluate the quality of the current state action pair. So basically, you can, for example, if we want to move here, we can move here, 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 here. So here, generate a series of state action pairs. And by updating this Q value, we can finally know this series of movement of this strategies is good or not. So how to update this Q value? We have these equations. It's based on the Bellman equation, and it's kind of straightforward. So basically, there are two blocks. The first one is the old value, and the second part is learned value. So the old value is the Q value we learned from the previous iterations. So this is kind of our experiences. And learned value is the value we learned from the previous iterations. And we have the alpha here. Alpha is the Q learning rate, which determines the weight given to new information over old information. So which is the old value and the learned value. And also we have gamma here. So the gamma is the discount factor, which determines the weight given to a short-term reward over future reward. In case you are not familiar with the Q-learning, you can check our papers. There are really detailed explanations on the theoretical part and all our implementations. So we want to apply the Q-learning to the site to design cost-effective countermeasures, and how to do that. So first, we want to, the most important part of this Q-learning is to design objective. We give an objective to the agent, and we want the agent to achieve this objective in an optimal way. So the first one, because we are doing the side channel, we want to design a cost-effective side channel countermeasure. So we want to first evaluate the cost of the countermeasure. So we have considered and simulate 4 types of countermeasure: the desynchronization, the Gaussian noise, the uniform noise, the clock jitter, and the random delay interrupt. So these 4 are the commonly used countermeasures in real life. And of course, there are more difficult countermeasures, but they can kind of be modeled with the combination of these 4. So we hope that this is just a pioneer work for the future deep learning-based countermeasure design. So for this hyperparameter choice, it's just based on our previous test 20 paper. And in case you are interested, you can check that paper, of course. And if for the potential users, this hyperparameter can be tuned, but this is just a demonstrations. For example, if we want to introduce the desynchronizations to the traces, the higher desynchronization level will introduce higher cost to the countermeasures. So after the combination of these 4 countermeasures, we can calculate the total cost of the countermeasure being implemented in the hardware. And we want to monitor this cost, and we want to control this cost. We want to make this cost as low as possible while giving us enough assurance that our hardware is secure. So how to do that? We designed such a reward function. It's not complex. I will explain. So there are two equations because we consider two different scenarios. So for the first scenario, we add the countermeasures. Well, this countermeasure is not strong enough. Then the security information can be retrieved by the deep learning attack. Then we use this equation. Well, if the added countermeasure is strong enough and the attack cannot be, we cannot perform a successful attack, we consider the second part. So let's move into the details about these notations. So this T prime, G prime 10, and G prime 50 are related to the effectiveness of the countermeasure. So imagine that we want to design a cost-effective countermeasures. So we consider first the effectiveness of countermeasures. So this T is the T prime is a percentage of the traces required to get guess entropy to 0 out of the fixed maximum attack traces set of traces. G prime 10 is the G value using 10% of the attack traces, and the G prime 50 is the guess entropy using the 50% of the attack traces. So as you can see here, if the attack is super successful, both these three values will be high, and in reflect to the reward functions, it will introduce us a low reward, which means that the countermeasures we introduce is not enough, it do not give enough insurance to the security. And another one, imagine that I just want to repeat that again, we want to design a cost-effective countermeasure. So another part is the cost of the countermeasures. So we have the state total, which I introduced in the previous slides. It's just a combination of the countermeasures, and we calculate the cost, and we introduce this Cmax. This is the threshold we want to give to the hardware, because we do not want the countermeasure go to infinite. Of course, it will give us enough security assurance, but it will just, I mean, make the hardware really power drain. So we set the maximum. So we want this value to be as small as possible. So the C prime can be as large as possible. So in this matter, we can have a higher reward. So by knowing this, we can have the overview of our countermeasure searching method. So we start by sampling the countermeasures, and then we train the network. Finally, we evaluate and update the Q value. The whole process is controlled by the epsilon Greeley schedule. So the epsilon Greeley schedule is balanced the exploration and exploitations. We start with the low value, so it can sample the countermeasures more randomly. And after the agent knowing the environment better, the epsilon will become higher, and the goal will change from exploring the environment to designing a good countermeasure. And also, because we want to design a good countermeasures, we found, well, according to the literature, which is the CHES 21 papers we present, we have this powerful convolutional neural network models that works for specific data set and leakage model. So basically, we use a reinforcement learning to design a countermeasure that to defeat the reinforcement learning based hyperparameter tuning model we designed. So yeah, so this is a model we considered. So here's the experimental result. We consider two data set, the ASCAD fixed key and ASCAD random key. Well, we want to know that the random ASCAD random key data set is more close to reality, because in reality, when you are doing the profiling attack, you normally come up with the profiling traces with random keys. But we, because this is just a standard for side channel community, we also consider ASCAD with a fixed key. So this is the ASCAD fixed key data set. This is just a searching overview of the different leakage model, and also a different attack model. So the RS means the reward small is just you can just consider it just a different type of convolutional neural network. So the plot here, let me interpret this. So the x-axis is the Q learning reward, and y-axis is the relative countermeasure cost. So we want this Q learning reward as high as possible, while this relative countermeasure cost as low as possible. So the countermeasure here will be the best countermeasure we want to choose. And also, of course, you can see the different color. It's just maybe you remember I just mentioned the epsilon gradient schedule. So we gradually increase the epsilon to moving from the exploration to exploitation. And the vertical line here indicates the highest Q learning reward for countermeasure set, which could not prevent the convolution neural network from retrieving the key within the configured number of attack traces. So this countermeasure is not working, while this is the highest one. So you can see that the Q learning reward, it gets just this countermeasure gives really Q learning reward. And this is searching, well, this is exploring, this is a reward plot for the different leakage model. So you can see that with higher iterations, the Q learning reward is gradually going up, which means that the agent is knowing start to learn from the environment, and gradually he or she maybe can design a better countermeasure. And the table on the bottom of the slide is the best countermeasure we observed or we obtained. So for the ASCAD with the Hemingway leakage model, surprisingly, the desynchronization with the desynchronization level 10 performs the best. So normally we consider that the convolutional neural network is pretty efficient in defeat the desynchronization of the traces. Well, in this searching, we show that with this specific setting, the desynchronization works pretty well. Well, for the rest of them, it's just a random delay interrupt with the specific settings works the best, which can be expected because the random delay interrupt really break the traces into a different split. And then for the neural network, it's really difficult to get attention on specific part of the traces and to classify and do the classification. And then we move to the ASCAD with the random key data set. We still have the different leakage model and also different models. And as I mentioned before, the neural network here in the right down corner, which is more closer to the right down color, will be the better cost effective countermeasure. And yeah, from this data set, we can clearly see that after iterations, the better countermeasure or cost-effective countermeasure can be obtained. And this is a result for the reward and also the countermeasure we obtained. So for this one, all of the best countermeasure is a random delay interrupt countermeasure, which proves that this type of countermeasure can be super strong. Well, we want to emphasize that although this is strong, the parameter, which is A and B and probability and amplitude. In case you are interested, you can check our paper. So for this hyperparameter, it's not really straightforward to tune, but our framework can effectively found this optimal parameters. Well, the countermeasure with the smallest cost. So finally, we move to the conclusion and future work. So in this paper, we propose a reinforcement learning framework that enable automated search for side-channel countermeasures combinations. We motivate and develop custom reward functions, and we demonstrate the effectiveness of our method. So for the future work, we want to benchmark our method with other methods such as dynamic programming, and we want to consider the LMP, and also found that it would be interesting to investigate if the reinforcement learning can be used to develop new countermeasures. The new countermeasures we here is the countermeasure we haven't seen before. So it's not just a combination of different countermeasures. Thank you for your attention. And in case you are interested, you can also check our the code in our GitHub page. Thank you. Any questions?
Thank you, Lichao. It seems that everyone is still shy, so I will ask a question. You are, if I understand correctly, you measure the you introduced the countermeasure, an artificial countermeasure. So you just modify the ASCII the dates.
Yeah.
How is that similar to the to actually doing the countermeasure in hardware? Is that accurate?
You mean designing such a countermeasure?
Yes.
So well, our work is based on the simulation, that's for sure. But for the hardware designing of, well, for the countermeasure design in the real product, they have specific parameter to tune. For example, if they want to switch up a noise engine running in parallel with the encryption algorithm, they can control their power. Well, this is a parameter they can tune, and they can be the input of our reinforcement learning framework. And also, for example, if they want to apply the random delay interrupt, which is also based on the literature, and we have seen that in the real product, they can also tune the randomness of their product. So based on the leakage, and acquire the leakage and run our framework.
So it sounds like it's quite representative of what the countermeasure. Good. And another question is, you showed that there seem to be some parameters that you chose for the cost function. How did you came up with these parameters? So,
yeah, that is kind of trivial because when we first start with the say max with the maximum, well, this the threshold of the cost of the countermeasures, and then we just divide them by the level of the countermeasures. Like we set it to max, for example, if we set the maximum level to 50, then we divide 5 by 50, and then this is kind of calculated. But in reality, of course, this parameter need to be tuned because this is just based on our simulations.
Yeah.
So
okay.
I have one quick question. So I think thanks for the talk. I mean, you mentioned about RL as a countermeasure strategy, and I think there was a previous test paper where you talked about RL being applied for attacking, or maybe like fine-tuning the hyperparameters for a better attack, right?
Yeah.
So how do you see RL versus RL in that case, right?
Yeah, so this is a spear and shield problem. So we want to use a strongest shield to defeat the strongest spear. So yeah, that is an interesting questions. And well, so normally if you want to design a good neural network with RL, you normally have the leakage traces. So the leakage traces is kind of fixed. So this is kind of the interactive process. You need to first come up with good countermeasures, then you can design a good neural network. And after you come up with a better neural network, you can design a better countermeasures. So, well, this is the interactive process, and I also see that it's in the side channel community.
Okay, thank you.
Yeah.
Okay. With no other questions, we'll move to the last presentation for today, for this session today. And this is the last paper is deep freezing attacks on capacitors and electronic circuits. The work will be presented by Jalil Morris, who is a senior undergraduate at Yale University, studying electrical engineering and computer science, and is currently looking for applying for a PhD degree. So good luck with the applications, and look forward for the presentation.
Thank you. So hello, everyone. Welcome. As Yuval mentioned, my name is Jalil Morris. I'm an undergraduate at Yale University in the US, and my presentation will be on deep freezing attacks on capacitors and electronic circuits. So this is joint work involving myself, Urbi, Anisul, Ferhat, and our advisor, Jakob. There we go. Okay. So as an introduction, my goal is to introduce a new research area which we are establishing, known as cryogenic security. The core ideas of our research are to leverage cryogenic freezing, typically performed using liquid nitrogen, to rapidly bring electronic components or computing devices to extremely low temperatures, approaching around -195 degrees Celsius. So our research goal is to develop new low-cost physical attacks and then design defenses against them once we examine their practicality and effectiveness. And then our motivation is that liquid nitrogen is typically inexpensive, so it makes it an easier way to attack the device. For example, manufacturers typically don't expect their devices to operate below -40°C, as specified on many data sheets. And liquid nitrogen, as I mentioned before, is inexpensive, costing around 10 cents. And it's also easily accessible, usually in clean rooms in any academic or research facility. And finally, there's no special equipment required for this type of attack, except maybe a container called a dewar for the actual liquid nitrogen. Oh, and so our research actually presents a new trade-off between the attack cost and the accuracy, which I'll explain in detail a little bit later. And so quickly, a history for using liquid nitrogen for security attacks. Actually, there isn't much prior work, at least in security, that uses liquid nitrogen. So for example, we have the first attack, which is the cold boot attack that uses an upside down computer dust spray to cool DRAM, allowing it to retain data over a longer period of time. This attack allowed the attacker to take the DRAM out of a computer and place it into another without significant data loss. And while liquid nitrogen was mentioned in the attack, it was only focused on the DRAM itself. And so recently, we also had a work that targeted capacitors and converters in using the same cooling sprays used in the cold boot attack, but also we did not use liquid nitrogen. Instead, we were focused on the effects of cooling the capacitors and their capacitance changes. And then finally, the work I'm discussing today on deep freezing attacks on capacitors and electronic circuits. We believe it's the first type of work to actually involve liquid nitrogen on capacitors. And so a quick outline of the rest of my presentation. I'll give background on physical security and physical attacks. And I'll also discuss our prior study of cooling effects on capacitors using cooling sprays. Then I'll talk about cryogenic freezing and attack types and also go over our security threat model. And then I'll go over our results on deep freezing attacks on capacitors, electronic filters, and energy storage capacitors. And then finally, I'll go over some research opportunities and give a short conclusion. So first, a little bit of background on physical security and physical attacks. Physical security considers attackers with physical access to the device, meaning the attacker can probe or manipulate the device in question. Usually this is difficult to defend against because the attacker has control over the device, but in practice, it can be pretty expensive and often requires specialized equipment in order to be effective. This idea implies some relationship, as you can see at the bottom, between the attack difficulty and the accuracy. For example, the laser fault injection, which you may know is an incredibly precise attack with the ability to flip bits in exact locations. However, it's known to be expensive with equipment costing around $10,000. A little bit of a more reasonable example is something like the chip whisperer, which can perform simpler attacks like clock glitching at a much lower cost. However, both of the examples that I just mentioned also require mobility of the device, meaning that it has to be moved and situated on a probe, which is usually not possible if the device is connected to some other external devices. And then finally, at the end of the spectrum, we have our liquid nitrogen attacks, which can be as inexpensive as around $1, but lacks the accuracy that some of the other methods have. And then now some information on our prior study of cooling effects on capacitors. So our motivation in this case was to target capacitors because they're basic elements found in most or even all types of electronic circuits. As I mentioned before, in this test, we use off-the-shelf electronic cooling sprays to cool down devices to about -51°C. And in our previous work, we usually sprayed devices for around 10 to 30 seconds in order to see the results. So on the right, you can see an image of how we actually performed some of the tests in our previous work. It's important to note that after some time, the frost dissipates and the device returns to its normal operation, eliminating all traces of the attack. And then here's some of our results. So our study centered around aluminum electrolytic capacitors because those were the ones frequently used in the converter circuits we were testing. Our previous results show that the capacitance can be changed, as in lowered up to about 10%, depending on the target. And we also show that there is some correlation between the capacitor size and the amount of capacitance change due to freezing. So we showed that the physically larger capacitors were actually less susceptible to change. So you can see in this graph here, the 50 voltage rating capacitor, which was the physically larger capacitor, was actually only able to be changed up to about 5–6%, while the smaller capacitor rated at 25 volts was able to be changed up to about 8%. And then to top it off, we also showed that these capacitance changes had an impact on the DC-DC converters that they were attached to. And now to go over our idea of cryogenic freezing attack types and our security threat model. So the motivation for our current work was to take our previous research a step further by adding deep freezing through liquid nitrogen. As I mentioned before, the liquid nitrogen can bring components down to low temperatures, reducing it to about -195 degrees Celsius. So we focused on two different attack types, pouring and dipping of the target device. So for pouring, obviously, we took the liquid nitrogen from the container and we poured it over the device. And then for dipping, we took the target device and dipped it in the liquid nitrogen for a specified period of time. We observed that the dipping attacks were much harder for what I mentioned before, because it requires the device to be moved and actually placed in the container, but it also achieved better cooling. Pouring, on the other hand, was less effective, but it was also easier. So our threat model was that the attacker has physical access to the device, but cannot modify the target, since it could easily be noticed or detected by onboard circuitry or certain fail-safes. So instead, the attacker has a small window, where say about 30 to 60 seconds to perform an attack, but they can control, for example, how long they decide to pour the device or dip it in the liquid nitrogen. And then while this attack can probably be detected through a thermal sensor targeting extreme temperatures, we did not find many such devices that incorporated in a defense against this. And then now some of our results on deep freezing attacks on capacitors, electronic filters, and some energy storage capacitors. So in our research, as I mentioned, we focus on two types of capacitors, electrolytic capacitors and supercapacitors. Electrolytics are polarized capacitors that use a wet or dry electrolyte. They can be made from aluminum, tantalum, or niobium. We focused on wet aluminum capacitors because they tend to be more widely used. And then another type of capacitor are the supercapacitors, which have higher capacitance values but tend to have lower voltage ratings. They're usually used in energy harvesting, as in for the storage part. And then due to the quick freezing, we observed that in both cases, the capacitance drops to at or near 0. So the graph below shows the results of various cooling on different capacitors using liquid nitrogen. Oops, sorry about that. So in general, the time to approach zero capacitance is correlated with the physical volume of the capacitor, meaning that for the same capacitance values, capacitors with a bigger voltage rating tend to have a bigger volume and subsequently tend to take longer to cool down. And then for the same reason, when warming up, since it took longer to cool down the physically bigger capacitors, it also took longer to regain normal operation since it had to be cooled for longer. And then the graph at the bottom shows the manufacturer, capacitance, voltage rating, and the actual casing size of the capacitor. In this case, T0 represents the time it took for the capacitor in that row to reach zero capacitance. And then T normal represents the time it took to return to a normal capacitance value. So here we demonstrated that the deep freezing is able to non-invasively shift the cutoff frequency in many of the electronic filters. We focused obviously on both high and low pass filters, and we're calling this a new cutoff frequency shifting attack. So by affecting the cutoff frequency, we're essentially inducing the wrong operation of these filters. So obviously, maybe low pass filters are no longer passing low signals, or high pass filters are no longer passing higher signals. Okay. So as a review, a high pass filter is an electronic filter that passes signals with a higher frequency than a certain cutoff frequency, and then attenuates signals with frequencies lower than that cutoff. So we observed that for a fixed input frequency, as freezing is applied to the capacitors and they freeze, the signal that should be passed begins to be attenuated. And then similarly, once the freezing stops, the capacitors slowly start to warm up. which means the time constant is able to return back to its original value, and the filter begins to pass the input signal again. And then similarly for low pass filters, since it passes lower frequencies, as the device is cooled, the cutoff increases. The cutoff increases and the signal will be passed as opposed to being attenuated under normal circumstances. And so for our evaluation setup, we use several first order high and low pass filters. Although it's not the standard, we used the same aluminum electrolytic capacitors to demonstrate the freezing impact on filters. And we designed filters primarily with a cutoff frequency of about 0.7 Hertz. And we sent an input of 1 Hertz just to more clearly recognize the results. So for pouring attacks on electronic filters, the pouring of liquid nitrogen can be used to modify the operation of the electronic filter, meaning that when you freeze the capacitor, it lowers the capacitance value, decreasing the RC constant, and then thus increasing the cutoff frequency to near infinite values. In the graph below, it shows the change in operation due to cooling over time. So the top is 30 seconds worth of cooling, and then the bottom is 10 seconds worth of cooling. As you can see, the bottom graph of 10 seconds is able to recover more quickly because it was cooled for a shorter amount of time. So in the graphs, the x-axis represents the time, where time 0 represents the time that the cooling was started. And after, let's say, 30 seconds for the top graph, the cooling was stopped and it was given time to warm up and recover. And then for the bottom graph, it was only cooled for 10 seconds. It stayed the same for a little while and then started to recover. And then at the same time, we also explore the same properties as the capacitor size as we did in our previous work. So for similarly, the bigger the capacitance or the bigger the voltage rating, we observed bigger capacitor casing sizes. And so in this test, we compared two capacitors, a 220 microfarad capacitor and a 470 microfarad capacitor. And so above, you can see the 220 capacitor took much longer to actually return to normal operation, even though the 470 capacitor was also cooled for the same amount of time. And then now we're showing the difference between the dipping version of the cryogenic freezing attack and the pouring version. So as I mentioned before, the dipping of components in liquid nitrogen compared to the pouring allows for lower temperatures in the same amount of time. But as I mentioned, it also requires placing the target in liquid nitrogen, which may be a little bit less practical. So in this example below, you can see we use the same 220 microfarad capacitor in both instances. However, the top one used the pouring method and the bottom used the dipping method for 30 seconds in both cases. And you can see the bottom one took significantly longer to recover just because the device was dipped in the liquid nitrogen instead of poured. And then our results on low pass filters and higher order filters. So since we tested both low and high pass filters, we noticed that the same effect sort of applied. So in the case of low pass filters, the signal was passed when the freezing was applied as opposed to being attenuated under normal operation. And then we also explored some higher order filters using multiple capacitors, where we froze one at a time or several at a time, depending on the test. And we noticed that the filters behaved very similar to the first order filters, where in the high order case, the signal was actually attenuated as opposed to being passed. And then finally, for deep freezing attack of energy storage capacitors, we evaluated 3 supercapacitors on an energy harvesting device as shown here with their names and capacitances. Here we used a program to charge the capacitors on the board and then allowed the energy to drain, reporting the time it took to completely drain the capacitor. And on the right, you can see an image of that sort of example. So we observed that there was about a 10 times reduction in runtime due to freezing, faster device crashes, and potential device damage due to freezing. As you can see in the table on the bottom left, the capacitor was able to power the board for a significantly shorter amount of time when frozen. Unfortunately, on the broken board at the bottom of the graph, we were not able to determine which component actually caused the failure, but we do know that the failure was due to the freezing. And then finally, in conclusion, we introduced a novel cryogenic free security research area and demonstrated a number of potential new security threats due to liquid nitrogen freezing, due to the extreme temperature drops and the change in behavior of the capacitors and the electronic filters. Unexpected operation was induced, causing failures or faults or other potential system glitches. And deep freezing effects quickly dissipate, eliminating most traces of the attack, making it a very viable attack. And then since this is a new research area, of course, we believe the idea can also be applied to many other devices that we are currently looking into, and we hope to have some more results shortly. And thank you, that is it.
Thank you very much, Jalil. And as usual, today we don't have many questions, but first questions, probably. You have demonstrated that you can change the parameters of electronic devices. Now, what can an attacker do with that?
So as I mentioned, I think in one of the earlier slides, we sort of have this trade-off where an attack is either extremely accurate, but also really costly, or not very accurate and thus obviously kind of inexpensive. So our threat model is sort of, you want to do this sort of cost-effective attack, just to use the same word as the previous talk. And the attacker is able to affect the operation, as in maybe cause some potential system glitches or maybe some faults, or just possibly the device won't stop functioning for a period of time. But the attacker isn't actually able to sort of attack a specified area of the actual function of the device.
Mm-hmm.
So in the term of filters that we demonstrated, you can see that even though the filter is supposed to pass or attenuate a signal according to the actual cutoff frequency, as you pour the liquid nitrogen, you can actually stop that function.
Cool. Thank you. Mainak, would you like to ask a question?
Yes, I do. Thanks, Yuval. Thanks, Jalil. That's a fantastic talk and pretty futuristic. Loved it. So I would actually build on Yuval's question, right? I mean, what is the efficacy of the attack, or how you, because I understand that you are starting this and it's a great avenue. So towards that, two questions actually. The first one is that how much of a cost decrease did you attain for doing similar attacks by state-of-the-art method? Like in terms of dollars, do you have any idea? Because I'm assuming that such attacks are expensive to do today without your technique. So how much of a cost decrease are you achieving?
So we actually did not examine exact cost numbers in relation to some of the other examples of some of the other physical security attacks, but that is an interesting question, and I actually would like to look into that a little bit more. So the examples I gave in the previous slide were sort of just some general ideas that we were able to come up with in order to compare to sort of go along the spectrum of this is extremely cost effective, this is extremely expensive, but we don't have any exact values.
Okay. And the second question, I guess it is also related to the first one and Yuval's question. So what you have shown is the potential to have some systematic way of controlling the behavior of the circuit, right? Using LN2, like something that you can predict or something that you can model. So using that, how do you feel that you can launch an actual attack? Like for example, for cold boot attack, which you have given as an example, or even power attack or timing attack, the idea is to get secret bits, right? Even the whole the Spectre attack and like everything, this is about getting the secret bits out of memory. That's the main goal for in those cases. For you, I was just wondering, how can you actually, or how do you think you want to evaluate the actual attack using this technique?
So I guess first I can start by saying that maybe the cold boot attack isn't a perfect way to sort of relate these two, because the cold boot attack is more of a data extraction sort of attack, where you're able to have access to another device's or another computer's data without sort of having permission. And then this is more of a malicious attack, where you're actually trying to cause some sort of data loss or some damage to the device with the liquid nitrogen, as opposed to actually targeting specific data. So I guess we sort of formulate our threat as a malicious attacker is trying to damage a particular device, and let's say maybe a data center somewhere, and causing a significant amount of data loss as a result of the attack.
So that is more like a akin to a denial of service attack, rather than a more surgical kind of attack, like where you extract the data or change the system, right?
Yeah.
Okay.
Yeah, so our attack isn't specifically trying to say that you have some sort of data that you want to attack. It's more of you just trying to stop the functionality for a period of time in order to cause some loss. And then I think, at least we think, the best part of this attack is that it's normally not very invasive. And then after that period of time, there are no traces of the attack. So it's hard to actually ascertain what happened.
Okay. Thanks, Eden. And just a last comment, I guess. You might have already looked into it, but you might want to also connect this work to the fault attack kind of work. If you have a way to systematically and in a principled way introduce faults, that can be really, really bad for security of the system.
That is a good idea. I'm actually hoping to write all these questions down and bring them back to my group, and obviously discuss them a little bit more. So if you have any further questions, I would actually like if you would send them to my email, so that I can we can actually continue on these topics.
Absolutely. Thanks.
Thank you.
That's all.
Thank you.
Thank you very much, Jalil. And there seem to be no further questions, so I would like to thank all speakers. I enjoyed this session, and I hope that everyone else enjoyed it. And with that, I guess we move to the next section.